Hello guys, let's have a look at the new question. Here we have a question dealing with the concept of simple harmonic motion. Let's begin with the question. A U-tube contains liquid as shown in the figure 3.1. The total length of the column of liquid in the tube is L. The column of liquid is displaced so that the change in height of the liquid in each arm of the U-tube is X as shown in the figure 3.2. Here we notice that as the liquid moves, there will be displacement, and the displacement is a value of X on the left hand side and also a value of X on the right hand side. The same can also mirror itself. Moving ahead, the liquid in the U-tube then oscillates with simple harmonic motion such that the acceleration A of the column is given by the expression A is equal to minus 2 into G over L into X, where G is the value of acceleration due to gravity and L is the total length of the column of liquid as stated before. Here, the keyword to notice is simple harmonic motion. And when an object is said to be in simple harmonic motion, there are three necessary conditions that it satisfies. 1, the body undergoes periodic motion. 2, the body undergoes oscillatory motion. And 3, more importantly, or more relevant to this question, the acceleration of the particle at any point is equal to minus omega square x, where omega is the angular velocity. So when I equate this standard equation A is equal to minus omega square x to the expression A is equal to minus 2g over L into x, I get to know that the constant omega square is equivalent to 2g over L. Moving on to part A, calculate the time period T of oscillation of the liquid column for a column length that is 19 centimeter. Now, we understand that the value of L is given to be 0.19 meter SI units. The value of G is a constant from the data booklet, known to be 9.81 meter per second square. We know that omega square is equivalent to 2g over L, and omega in terms of time period is written as 2 pi over t. So the equation becomes 2 pi over t the whole square is equivalent to 2g over L. Here, 2 and pi are constants. G is also a constant whose value is known to be 9.81 meter per second square, and L, the only variable, is 0.19 meter. With all the values known, we rewrite the equation in terms of t, and when substituted and simplified, we get the value of t to be approximately 0.62 seconds. Moving on to part B of the question. The variation with time t of the displacement x is as shown in the figure 3.3. Now, before we make further observations, let us first take a closer look at the graph. The graph seems to be having equal time periods, but the value of amplitude keeps on decreasing. This is a typical characteristic of a damped oscillation. So in a simple harmonic motion, or when a body executes simple harmonic motion, in an ideal condition, we assume the amplitude to be a constant or the maximum displacement to be a constant. But if the maximum displacement or the amplitude periodically keeps on decreasing over time, such an oscillation is called a damped oscillation. And the specific characteristic of a damped oscillation is the fact that a resistive force reduces the amplitude periodically. Moving ahead, the period of the oscillation of the liquid column of mass 18 gram is T. So we have the value of mass M, which is 0.018 kilogram. Moving ahead, the oscillations are damped as stated. State one cause for the damping. Here we notice that the liquid moves up and down a U-tube, and the only form of resistive force we can ascertain from this is the fact that the walls of the liquid apply a viscous or a drag force on the liquid, which is known as viscosity. And this is the particular reason why the oscillations are damped. So one reason we can positively state for the reason of damping is the viscosity or the viscous drag force, also known as friction between the walls of the container and the liquid. Moving on to part 2, calculate the loss in total energy of the oscillations during the first 2.5 periods of oscillations. Now, we ascertain that one complete period is from one peak to another. This is the second time period, whereas this is exactly 2.5 time periods. The amplitude at the initial point is exactly 2 centimeter, while we notice here that the amplitude is approximately minus 0.95 centimeter. Now, we will first help derive an equation for total energy of the oscillations. We know that the kinetic energy is given by the formula Ke is equal to half mv square, where velocity v in simple harmonic is given by half times m times omega square into x naught the whole square minus x square. Here m is the mass of the body, omega square, where omega stands for angular velocity, as explained before. X naught is the maximum displacement, and x is the value of displacement at time t. The value of total energy is nothing but the value of maximum kinetic energy. And we know that maximum kinetic energy is obtained exactly when the value of displacement x becomes equal to 0, or at the mean position. By that logic, the value of total energy becomes half m omega square x naught square, where x naught stands for the maximum displacement at that point. At 2 centimeters, we just need to substitute the value of x naught as 0.02 meters, and at minus 0.95 centimeters, we need to substitute the value of x naught at minus 0.95 centimeters. We can find out the total energy at this first instant and also at this instant of 2.5 time periods. And the subtraction between them will give us the loss of energy as approximately equal to 2.9 into 10 to the power of minus 4 joule. This concludes the solution to the question. Thank you.